selected by Bartlomiej. So Bartek, please.
Thank you very much. Hope everyone is still here. So I'm interested in barrier phases because I'm interested in ADS CFD, and there are a powerful tool there. So let's talk about what we need to know from ADS CFD to appreciate the use of barrier phases or barrier connections. Of course, ADS CFD is an equivalence between two cylinders. A hollow cylinder is where a conformal field theory lives. A solid cylinder is where gravity happens. We call it the bulk. And these two descriptions, CFD on the hollow one and gravity in a solid cylinder, are supposed to be equivalent. For me, a very important a fundamental thing of fundamental importance is will be Ryuta-Kayanagi surfaces. So what are they? Let's focus on an equal time slice of a geometry, assuming that we have at least time reversal symmetry. Ideally, maybe the geometry is static, but at least time reversal symmetric. And I'm going to take an equal time slice of a geometry. On that equal time slice, and I'm sorry for being so mundane about reviewing things that have been talked about a lot in the last week, but it's probably useful to set everybody on the same page. So I'm going to take an equal time slice of this geometry and divide it into two pieces. One of them I will call A and the other one A complement. And on that equal time slice lives some state of the CFD, because that's I'm taking an equal time slice when I should have said it this way. When I take an equal time slice of the hollow cylinders, if I take the equal time slice of the boundary, then this is where a state of a CFD lives. See, the state of a CFD lives on Cauchy slices of the hollow cylinder, and these are circles like this one. So that's where a state like psi lives in HCFD. And I assume that this Hilbert space factorizes into an A Hilbert space and an A bar Hilbert space. This is not an assumption which really is true in realistic holographic theories, but I will make it anyway. The details of this are probably not important for our purposes, the subtleties. So I will define rho A, the reduced density matrix of A, to be take psi psi, the outer product. This is an operator now, a projector onto the state psi, and I will trace out the part of the Hilbert space which corresponds to A bar, the complement of A. This operation only makes sense when I have a product, tensor product factorization of the Hilbert space. And if I don't, then I have to be more careful about what I mean by the reduced density matrix on A. But again, that subtlety will not really play a role for us. So now I have defined a reduced density matrix on A. This is an operator that acts on just the Hilbert space on A. It acts here. I can take a quantity called the von Neumann entropy, which is just minus the trace of rho log rho, or rho defined this way. And this is what we call the entanglement entropy of A. And it's some measure of the entanglement between A and A bar. So an amazing statement that we owe to Ryu and Takayanagi from now almost 15 years ago is that in the bulk, in the gravitational description in the solid cylinder, when I take an extremal area, or really limiting to this just equal time slice surfaces a minimal area, which asymptotes to the border of A and A bar, that's what I mean by this, then the surface area of this extremal area in units of 4G Newton is equal to this number, to the von Neumann entropy of A and A bar. And this is the Ryuta-Kayanagi proposal. It will be very important for us. So having made this statement, the next question you can ask is, if I only know rho A, so if I only trace out A bar and I don't know anything about A bar anymore, but only this rho A, it's an operator in the CFD Hilbert space, but only the A part, how much of the bulk can I reconstruct? And this is known as subregion duality or subregion reconstruction. And the answer to this question is something called the entanglement wedge. So what is an entanglement wedge? Roughly speaking, it's the region of the bulk which lives between the Ryuta-Kayanagi surface and the region A, which is in the hollow cylinder, which is on the boundary of the whole cylinder. everything in between, plus stuff which is causally related to in some fashion to this piece of the bulk time slice. There is some more complicated description or definition of what an entanglement wedge really is. But for our purposes, the important part is that it lives between the RT surface and the A part of the CFT Cauchy slice. Plus, it is stuff which is bounded by null sheets that go out of the RT surface. This description that I just gave you, that I can just take the RT surface and take stuff which is space-like separated on the A side from the RT surface from it, is not globally correct, but it is locally correct if I'm close enough to the RT surface. If I'm close enough to the RT surface, this is a correct way, an okay way of specifying, of describing what the entanglement wedge is. Now, but in general, farther away from the RT surface, some complications show up. Sometimes we are in a lucky situation where the complications never show up, and what I just told you is globally true. That globally the entanglement wedge can be described by null sheets that emanate from the RT surface. When does this happen? Well, when this happens, the entanglement wedge is the same as ADS Rindler space. So let me just remind you what Rindler spaces are. Here's a picture of 1+1 dimensional Minkowski space. If I consider accelerating observers, their trajectories look like this, and then these accelerating observers divide the space-time, this 1+1 dimensional space-time, into 4 pieces. This is a piece that they can neither see nor influence. This is a piece which they can influence, but they can never see it because they never can look back along a time like a null trajectory and look what's inside there. There is a piece that they can see in their past, but they couldn't influence. And then there is one piece which they can both see and influence. These 4 quadrants, 2 of them are called Rindler wedges, and the other 2 are called Milne wedges. So Rindler space is the space that a bunch of accelerating observers can both see and influence. And in the lucky situation where no complications arise and the entanglement wedge is really bounded globally by null sheets, in that case, the entanglement wedge is literally like Rindler space, only in the ADS context. It is also the part of ADS spacetime which can be both seen and influenced by a family of accelerating observers. When does this lucky situation occur? It occurs, for example, for spherical regions in the vacuum. It also occurs for intervals in any locally pure ADS-free geometry, for example, in BTZ black holes. However, it does not happen in general. So we have to remember that what I just told you about Rindler spaces is just an aid in visualization in general. However, it is really true close enough to the RT surface. If I'm close enough to the RT surface, I might as well pretend that the entanglement wedge is a Rindler space. Farther away, that will just break down, but close enough, it's okay. And so yes, this is the statement I'm making here. The accelerating observers picture is always useful if I'm near enough the RT surface. So here's a picture of an entanglement wedge. I have some RT surface. I drew null lines which are orthogonal, null trajectories which are orthogonal to the RT surface at the endpoints. And then I drew these arrows here which correspond to the motion of an accelerating observer for whom the RT surface is the horizon. This kind of Rindler horizon is the same as our RT surface. So when I zoom in on this picture, it looks like this. Here's an RT surface. Here are these 2 null sheets, and I drew 2 accelerating trajectories. If I project out the RT directions out of it, and I just look at the 1+1 dimensional piece of this picture, it looks like this. And then it's literally Rindler space we're talking about. So this is a sliver where the accelerating observer's picture works. Okay. What I mean by this sliver is that I have to be close enough to the RT surface. So this region here is the region where I can talk about these accelerating observers and treat the entanglement wedge as a Rindler space. When I go farther away from the RT surface, it will break down. But notice that the region which is close enough to the RT surface always has this shape. Okay. Why does it have always this shape? Because I'm bounding the region where the description is valid by some invariant Minkowski distance from the RT surface. And that's a statement, okay, and points which are close enough to the RT surface in the Minkowski metric are the points that are bounded by this hyperbola, okay? So this point is just as near from the RT surface as this point. They both have very small invariant distances, yes? Going away along this direction is incurring zero distance in the Minkowski metric. So it looks like the sliver is getting longer and longer and very large, but remember that points that live all the way there are actually zero or near zero distance from the RT surface. And the sliver where the description with the Rindler description is valid will always have this shape transversely and follow the RT surface longitudinally like this. So that's the picture we have drawn here. This and this are the boundaries of the slivers where the Rindler description of the entanglement wedge is valid. Okay, so here are some facts that just regurgitate what I said. Where I can treat the entanglement wedge as approximately Rindler space, that region always hugs the boundary of the entanglement wedge along these null sheets, like here and here. And then it extends along light sheets because near the RT surface, the distance is very small as I'm almost following a null sheet. So that's this statement here. And you can say, well, what is the size of this region? So what controls the invariant distance between any point here and the point on the RT surface? And the answer is that in higher dimensions, what controls it is are the eigenvalues of the extrinsic curvature tensor for the extremal surface. And so remember that an extremal surface is specified by the condition that the trace of the extrinsic curvature tensor is zero. But the trace means that individual eigenvalues can be non-zero. They just have to add up to zero. And so the individual eigenvalues set the distance at which this accelerating observer's description will break down. And we know these facts from a paper by Aitor Lewkowicz and Tom Faulkner, which I will include in my references tomorrow. So for us, the important thing is that the individual eigenvalues of K control the size of the lucky region where I can treat the entanglement wedge as if it was Rindler space. And yes, any questions about this? So if there are no questions, then I will need to make one more necessary digression to proceed, which is the accelerating observer's picture. This is really strictly speaking valid in the code subspace. So what is this thing about the code subspace and about error correction? Suppose that I take an equal time slice of my geometry. So this piece of the geometry, just an equal time slice, this disk, and I divide it into 3 pieces, A, B, and C. And I ask, what is the entanglement wedge of AB? Well, it's everything that lives above this line. So this is it. And then what is the entanglement wedge of AC? It's everything that lives to the left of this line. This is the AC entanglement wedge, cross-section of it. What is the BC entanglement wedge? The cross-section of it. It's this region, yes. So we find that this point lives both in the entanglement wedge of AB and of AC and of BC. But there is no operator which simultaneously is part of the acts on the Hilbert space of just AB and on AC and on BC. There's no such operator. So either I'm acting on AB, that means that my action is trivial on C. If my action is trivial on C, then my action on AC is really bounded just on A. But if my action is just limited to A, then I have no action on BC. That's the statement I'm making here. So that whenever we say that knowing rho AB, remember rho AB is an operator that acts on HAB. Rho AC is an operator that acts on HAC. Rho BC is an operator that acts on BC. Whenever I say that knowing these operators allows me to reconstruct these entanglement wedges, that should mean that I should be able to reconstruct this operator But then this operator would be acting on AB or on AC or on BC, and there is no such operator. So there must be something wrong with the statement that knowing rho allows me to reconstruct these entanglement wedges. So is subregion duality wrong? And the answer is we must be meaning it in some more subtle sense. And so the subtle sense is that there is a linear subspace of the full Hilbert space, which we call the code subspace. And the statement is that I can reconstruct an operator that lives here in 3 different ways, one that works in AB, one that works in AC, and one that works in BC. But all those reconstructions will have the same matrix elements inside states which live in this code subspace. So I just care about reproducing expectation values of operators inside wedged between states that live here. Whereas states that don't live in the code subspace, on those states, the operators, the different putative reconstructions of the operator here will have different expectation values, and that's okay. They're only supposed to be to give me the correct and consistent description when I restrict my attention to this special space, which is a code subspace. Okay, so the code subspace, the relevant code subspace of interest for us, and generally how people use it, is the code subspace that contains low energy effective fields inside ADS. But for example, it would exclude stringy stuff. Well, that's a logical and practical way of defining what I mean by the code subspace. So I just want to say that from now on, whenever I say, for example, H, I will really mean taking H and projecting it onto the code subspace. And from now on, everything that I will say in my ADS CFT discussion is always going to be, I will always implicitly assume that I have projected onto the code subspace so that I don't run into these problems of ambiguous reconstructions, and also so that I can freely use the language of low energy effective field theory in the bulk of ADS. Are there any questions or comments about that? About the digression or anything else before that?
So again, you're assuming this factorization of the Hilbert spaces, right?
Yeah, so I was just saying a few slides ago that this subtlety that this equation is really not true, it just doesn't matter. So I'm trying to be, I am willingly and willfully skipping that subtlety and assuming that it won't cause us problems. We can have a discussion for experts about whether that's a valid assumption, but for the purposes of these pedagogical talks, I will just not worry about the factorization problem.
Right. Yeah. I just mentioned it because I'm just wondering whether it affects the question of whether this operator exists or not. Right. That you mentioned that is in all these 3 regions.
You mean this one?
Yes.
Surely it affects it because these concepts, HAB, HAC, and HBC are not defined if they don't have it. But right. It is, so whatever breaks the factorization has to be a pretty subtle effect, because to the extent to which we can use low energy effective field theory in the bulk of ADS, if that field theory doesn't have gauge fields, and I don't think that we are forced to consider gauge fields, then such a Hilbert space really would factorize. So to the extent to which I don't have gauge fields in the bulk, I would just go ahead and use the factorized Hilbert space in the bulk language. And then I would ask, well, okay, so how do I reconstruct this bulk operator in the well-defined bulk Hilbert space? And the point is that there are these vastly different reconstructions. There is a reconstruction that is supported only here, and there is a reconstruction that's supported over here. Now, maybe those reconstructions have some small tails, which come from the fact that I didn't actually have a factorization, so I couldn't properly just limit my reconstruction to BC. Maybe it spills over into A a little bit, but even if it does, it will spill over in some small fashion. This is a subtle effect. It's not an order 1 effect. And so the question just becomes, how is it that I can have more than one reconstruction and they are macroscopically different? And that's what this thing is supposed to answer. I think that the problem arises even if I don't assume factorization in the boundary. Okay, so let's give a summary thus far of what we have said. This is a picture of the entanglement wedge, the part of it that we have control over. It's a sliver of, so first of all, there is a Ryuta-Kayanagi surface, which is a minimal surface that defines the part of the bulk that's contiguous to A, and the part of the bulk that's contiguous to a complement. I divided the slice into two pieces. I have, before that even, I assumed that I had time reversal symmetry, so I could talk about unambiguously about the bulk slice. The picture does have a generalization for cases that are not time reversal symmetric, so this is not an essential assumption. It's just meant to simplify life. So anyway, I have this division of the bulk slice into two pieces, and the division itself, the border between them, is the Ryuta-Kayanagi surface. Light sheets that go away from it define for me a boundary of the entanglement wedge. Farther away from the RT surface, this picture sort of breaks down, and I have stuff that violates that doesn't conform to my favorite language of accelerating observers for whom the RT surface is their acceleration horizon, but that happens farther away. Locally near the RT surface, I can just think of null sheets as defining, carving out one piece of ADS space and calling that the entanglement wedge. I stress the locality, however, because it is definitely majorly wrong to extrapolate it everywhere away from the RT surface. Okay. In the CFT, we defined an object called rho A, the reduced density matrix on A, by tracing out A bar. And the statement is that the information in rho A in the CFT and all information about this entanglement wedge of A are equivalent to each other. There is an ADS CFT type duality or entry in the dictionary that takes this and spills out that, or vice versa. So knowing this, reconstruct the entanglement wedge of A. Okay, and then we knew that the area of the RT surface in units on 4G is the entanglement entropy, and it equals to minus the von Neumann entropy of this density matrix rho A. And we further know that in the code subspace, the entanglement wedge has a near RT surface symmetry. That symmetry ceases to be a good symmetry away, but close to the RT surface, there is a symmetry, which is just a symmetry of this picture. This picture, as is well known, has an SO1,1 symmetry, which corresponds to the boosts that keep this point fixed. There is just the same type of symmetry over here, which allows me to follow these accelerating observers' trajectories. And so I can view the trajectories of the accelerating observers as orbits of a symmetry. What is that symmetry? It's a local boost symmetry. And like I said, further away from the RT surface, I no longer have this symmetry, but close enough to the RT surface, I do. And that boost symmetry that I have, so orbits of it are trajectories of accelerating observers for whom the RT surface is the horizon. This boost symmetry, I can ask what generates this symmetry. And the answer is that it's generated by the modular Hamiltonian, which is minus log rho A. It's minus the logarithm of the density matrix I had here. And this guy is called the modular Hamiltonian, the generator of the approximate boost symmetry in the neighborhood of the RT surface. This is an approximate symmetry of the, well, calling it the boost is approximately true, and the approximation improves the closer I get to the RT surface. But the symmetry itself is defined everywhere, because by definition, if I take a rho A and I take minus the logarithm of it, this H mod is going to commute with rho A. The fact that it commutes with rho A means that if I could, from rho A, recover the entire entanglement wedge, that means that, well, it's a symmetry of the entanglement wedge. Yes, it's a symmetry of the object which entirely reconstructs for me the entanglement wedge of A. So there is always a symmetry of the entanglement wedge, which is generated by H mod. It just doesn't always take the form of a boost. However, it takes the form of a boost when I'm close enough to the RT surface. So that's the way to read this statement. We have an exact symmetry of the entanglement wedge, which acts in some messed up way farther away from the RT surface. But when I'm close enough to the RT surface, the symmetry simplifies and it just becomes a boost symmetry. Is that statement clear and okay? Okay. So, right. And this goes back to something I just said a moment ago, but let's ponder this statement, this equation for a little bit. Rho A, by our definition that we just made, is equal to e to the minus h mod. So what does it mean that we chose this Hamiltonian? It means that we chose some operator and we called it a Hamiltonian so that our density matrix would be thermal. Yes, a thermal density matrix is e to the negative beta h. Here I'm choosing beta to be equal to 1, but okay. But the beta isn't really physically significant at this point. H mod is an operator such that if I chose it to be the Hamiltonian, then this density matrix would be thermal. Yes, it's thermal with temperature 1 in this case. And here I just have a note that some authors like to insert an extra 2 pi here so that the temperature becomes 1 over 2 pi for reasons that have to do with analytically continuing this picture to the Euclidean space, and then you would want a periodicity to be 2 pi for the circles that are generated by the analytic continuation of these hyperbolae. That's a choice that you can make, but that won't be important for us. So notice that we chose this H mod so that rho A would look thermal with respect to it, but whenever we have thermal states, thermality on the CFT side is typically related to horizons in the bulk of ADS. So an example of this is an ADS Schwarzschild geometry. This is the Penrose diagram, but if I draw it in terms of a cylinder, it really looks like this. There's some horizon at some fixed radius where I cannot fall inside. A single-sided black hole looks like this. And the statement is that the fact that I have a thermal state means that going very straight at in the time direction, but staying at an equal radial direction is really an accelerating trajectory. That acceleration is just like this boost, the trajectory of this accelerating trajectory here is really just like this trajectory of the boost symmetry here. I'm staying at a constant distance away from what the horizon is here. And here I'm staying at a constant distance away from what the horizon is here. And staying at a constant distance means accelerating, okay? And that boost symmetry here, from this point of view, is really just time translations that allow me to go from here to here to here and further on. So we define the Hamiltonian so that for our entanglement wedge, all the same intuitions that we have about black holes from this picture would carry over. And yes, so we define a Hamiltonian so that our horizon has the same thermal description. But again, we have to remember that the boost symmetry generated by H mod really only is a boost near the RT surface, and farther away, H mod will act non-locally. Before I go on to actually discussing modular Berry phases, I need to say one more thing. And that one more thing is about modes of the modular Hamiltonian. So when we have a simple Hamiltonian or a simple, when we have a simple Hamiltonian such as ddt, which is time invariant, which is fixed, then what we like to do is decompose any time-dependent operator, let's say, into frequencies. This is what's called Fourier analysis, yes? So in a similar fashion, we can take some operator which acts in the entanglement wedge, and we can decompose it into Fourier modes with respect to H mod. And the way we do it is we find a basis of operators which satisfy this eigenvalue equation. Namely, if I time evolve the operator with H mod by some infinitesimal time, that's what's given by minus I commutator H and O, then I get the same O with some eigenvalue. And that eigenvalue is what we would call the modular frequency of that component of the operator, of this basis operator. This lambda here in this equation is typically imaginary. And so, for example, just to give ourselves an intuition about this, let's say that our modular Hamiltonian, let's say that I was able to decompose it to diagonalize it, to write it in terms of modular energy eigenvectors, modular energy eigenstates. So then the modular Hamiltonian would take this form. I emphasize that when I write En here, I don't mean the energy eigenstates for the global states. These are eigenstates of whatever modular Hamiltonian was. So whatever diagonalizes minus the logarithm of rho A. Yes. But let's say that I found such a diagonal description, then a good basis for these operators which have definite modular frequencies would be something that takes a state, the M state, and maps it to the N state. Yes, it's some off diagonal element. What would be the eigenvalue under this commutation here for such an operator? The eigenvalue is just I times the difference between the energies of the states. Is that clear or not? So if I plug in this and this into this equation, I will get that the eigenvalue is this. So the punchline here is that just like we use Fourier analysis in real life or in ordinary daily life, and for example, we decompose signals into frequencies, or maybe we decompose whatever varies spatially into different wavelengths. In a similar fashion, now that we have a modular Hamiltonian, we can decompose operators into modular frequencies. And decomposing that is really equivalent to rewriting an operator in terms of this eigenbasis of this equation for different values of lambda. And I can think of lambdas as being I times the differences between the different energy, modular energies. And there is an interesting statement about such decompositions. Let's say that I decomposed an operator into these modular eigenmodes, and I just picked out a modular zero mode. The statement that we owe again to some combination of Tom Faulkner and Aitor Lewkowicz and collaborators is that the zero mode piece of an operator is the piece that localizes just on the RT surface. In other words, when we do this entanglement wedge decomposition, we may want to rewrite an operator inside in the language of operators that live in the CFT. How would we find which operators live where? Well, one statement that is very easy to state is that if I find operators that commute with the modular Hamiltonian, they are zero. We call them modular zero modes because they have a zero eigenvalue in this equation here. Then those operators are the only ones that have a chance of localizing on the RT surface here. So, and why is that? Because the RT surface is the only place which is stabilized by the modular Hamiltonian generated boost symmetry. Everything else transforms, but the RT surface stays under the boost symmetry, stays fixed. Yes.
So is there a relation between the eigenvalues and the distance, like, I mean, from the RT surface?
I don't know that there is an explicit paper that establishes that, but there should be. I agree with the intuition. Yeah, that's right. Yeah, I mean, okay, well, I'm not going to answer more this question because it will just take me on a tangent. But I think it's probably useful to think of these modular frequencies as being related to how far away we are from the RT surface. Okay, so in some cases it will be useful. It's a subtle statement, but yeah. Okay, so let's. So this ends the piece where I review what I need from the ADS CFT correspondence. Again, I hope that this wasn't too mundane, but hopefully I said a thing or two that at least some people haven't thought about recently. So sorry for the repetitiveness of this, but now we move on to stuff that probably you have not seen. So modular Berry phases. And this is just a reminder of what we're talking about. So the quintessential example of a Berry phase is that I have a spin in a magnetic field and I'm varying the direction of the magnetic field. The spin started in a ground state. It was anti-aligned with the magnetic field. Now it just follows the magnetic field. And after I changed the modular Hamiltonian, did it pick up some extra phase? That was the Berry phase. Okay, so why is this setup related at all to the stuff that I talked about a moment ago? And the answer is these Hamiltonians that Berry liked, there is nothing stopping us from taking modular Hamiltonians from the previous discussion and repeating it. So modular Hamiltonians are just like any other Hamiltonians in the world, and we can also vary them. And when we vary them, we should expect that there should be some Berry phases associated with them. Now, it's a little, if we just take literally Berry's discussion and carbon copy it to the ADS-CFT context, it doesn't buy us all that much. So it turns out that we have to take Berry's discussion and upgrade it a little to fully harness the power of varying modular Hamiltonians in the ADS-CFT context. So in the remaining 20-something minutes that I have now, I'm going to discuss just the right generalization of Berry's setup that allows us to vary modular Hamiltonians and extract a lot of information about the bulk this way. And remember that when we are varying these modular Hamiltonians, we're really taking some symmetry of a small neighborhood of the RT surface, and then we're changing that symmetry slightly. And changing that symmetry slightly could mean actually changing the minimal surface and moving it over in some way. And so that's what we will be doing. And and this I should emphasize here that when we are changing modular Hamiltonians, the change can really originate from two different things. One is that I can just change the state altogether. Of course, this changes the modular Hamiltonians, but I will focus on a more subtle way of changing things, which is I'm going to keep the same global state. This means that we're always living in the same ADS geometry. So this cylinder is unchanged. I'm just varying for which region the modular Hamiltonian is being computed. So I'm just changing the region A here. So A is minus log of trace A complement of psi. I am varying this A. I'm varying this A complement, and this gives me different ways in which I could have approximate boost symmetries, different approximate boost symmetries that apply to the same global geometry. Any questions or comments about that? So here's a picture. There's an A1, there's an A2. Each of them comes with its own modular Hamiltonian. And I'm asking, what happens? Is there a Berry phase associated with taking the symmetry of this RT surface, so the boost in the neighborhood of this surface, and mapping it to the boost in that RT surface? And mapping from the one boost to the other boost is really changing Hamiltonians the same way that Berry was changing his Hamiltonians. So the same type of discussion should apply there. Okay, so I promised that this language of fiber bundles was going to be most practical for it. So here I drew a fiber bundle again. And just like for the Berry case, we had to talk about what is the base and what is the fiber. We have to repeat the discussion here. So now I declare that my base will literally be the space of modular Hamiltonians. It's not just the space of ground states or projections onto ground states like it was in the Berry discussion. Now I literally want different modular Hamiltonians to form my base. It's a little bit like that psi-psi thing that we had in the Berry case. Now, when would this be the case? Imagine that I had a modular Hamiltonian whose eigenvalues were 0 for one state and just infinity everywhere. Well, if it's 0 and infinity, then the infinity would kill off all states. And so for all practical purposes, that kind of modular Hamiltonian would just act like a projector here. So going from projectors to modular Hamiltonians is no big deal. Okay. Now, and then what are the fibers? So the statement I want to make is that the fibers will be things that commute with H mod. And I will call these things modular zero modes, or I will call them, okay, so what are they? By definition, they are modular zero modes. because remember, modular zero modes are the things that commute with H mod. Now, I will also call them modular frames for reasons that I will explain later. But this is what the fiber directions will be. And then I can ask, is that a consistent way of generalizing Berry? And the answer is yes, because let me ask you, what commutes with this phi? Well, what commutes with this phi is a phase change of phi, yes? If I try to change phi by a phase, I'm not actually changing the projector, yes? This guy gets dressed by e to the minus I gamma, but the bra gets dressed by e to the plus I gamma, so the phases don't change the projectors. So when we previously used phases to span fibers, it's consistent to generalize phases to just things that don't change modular Hamiltonians. In other words, to the zero modes of the modular Hamiltonian. Is that okay? Okay, so, oh, this is just what I was saying here. So zero modes are symmetries of rho A. Okay. Now, how do I think about these symmetries? So remember that H mod is generates this approximate boost symmetry over here. Yes. So when I take so I should be let's be very careful about what this meaning of zero modes of the RT surface is. It's an approximate well, actually it's an exact symmetry of the whole entanglement wedge, but it looks like H mod looks like a boost symmetry close enough to the RT surface. The fact that this is a symmetry doesn't mean that it does nothing to the entanglement wedge. It means that it takes, for example, the point that I marked X and maps it to the point which I mapped like a circle. So a zero mode of an RT surface, whether it be the H mod itself, obviously H mod is a zero mode of itself, it commutes with itself. But if I have other operators that commute with H mod, they're also zero modes. Every one of them is a symmetry of the entanglement wedge, but it doesn't mean that it just does nothing. It means that it can take one, for example, an operator at one location in the entanglement wedge and map it to another location in the entanglement wedge, okay? So the symmetry doesn't preserve individual operators inside the entanglement wedge of A, but it preserves their expectation values. So for example, trace rho A of an operator at X here is the same as trace rho A with an operator at this circular location here, the circle mark location. They have the same expectation values in rho A. This means that if you just give me rho A and tell me this is all the data you have, then I will never be able to distinguish OX from OA because they are related by a zero mode of rho A. They're related by something that commutes with rho A. But it doesn't mean that they are the same operator. If we tried them, OX and OA, in some different entanglement wedge, or with some different density matrix, then they would actually act differently. They just look the same as far as this specific entanglement wedge is concerned. And so that's the kind of symmetry that we're interested in. So modular frames are the different ways in which operators that look identical in my specific entanglement wedge are related to each other. But I have to remember that these are actually distinct operators, and in other states they would be distinguishable. They just happen to be indistinguishable in my particular state. And these different ways in which such operators can be related to each other are called modular frames. And hopefully now that it is clear why I'm using the phrase modular frame. It's a frame-dependent statement that this operator, whether I'm talking about this operator or that operator, so long as I'm staying in the same density matrix, because they have exactly the same expectation values. They do become different, however, if I tried them in a different state. But in my state, in my rho A, this is just a change of frame because the physics here and the physics here is the same. Does that make some sense? Okay, so modular frames tell you which operators with identical expectation values are which in a given state. And changing modular frames means reshuffling among one another the different operators which have the same expectation values in rho A. So going from this O to this O, if they have the same expectation values, is really a change of modular frame. Notice that this is very much like changing phases for phi, okay? If I have some operator, and if I want to compute its expectation value in the state phi, and then I could say, well, what if I change the phase of phi? Yes. Well, if I change the phase of phi, then that would mean that I dressed my O with e to the minus I gamma on one side and e to the plus I gamma on the other side. Yes. So dressing O by a modular frame change for psi, this is actually a different operator from the previous one, okay? But it must have the same expectation values. So writing the equation this way should make it clear that changing modular frames is really like going to the Heisenberg picture with respect to H mod, because I am taking H mod and I'm taking something which, well, I'm really taking H mod and I'm taking some finite exponential of H mod here and dressing the operator by e to the minus and e to the plus I times that H mod on the two sides. So a very good way of thinking about what changing modular frames is and going from here to here is really dressing the operator by exponentials of H mod or whatever other things commute with H mod. That's really just like going to the Heisenberg picture with respect to H mod. So that's what the different modular frames are. Different modular frames are like different equivalent operators in different Heisenberg frames. Any questions or comments about this? So so this is a picture that we should have in mind at all times. The kind of setup is the same as the setup we had for Berry phases, but now in the base I have different modular Hamiltonians. I'm going from one modular Hamiltonian to a second one, to a third one, to a fourth one, and so on. I'm going to form some closed loops. And then I imagine that I started in some arbitrary modular frame. So I have some particular, my favorite set of operators that I will track. And you might say, which operators are they? There are lots of operators like that, which are related to each other by zero modes of H mod. And I would say, yes, but I just chose some very particular set. That very particular set is a choice of modular frame. And then the question is, my favorite set of operators, my favorite basis of all operators, how does it move over to a basis, to my new favorite basis of operators when I go to H mod 2 and then to H mod 3? And then after I made a closed loop, did my favorite basis of operators, did it come back to itself or did it come back transformed up to some transformation? What would that transformation be? Whatever it is, it has to be something that commutes with H mod. It must be just a change of modular frame. So it's possible that I have my favorite operator and then I applied modular parallel transport, made a closed loop, and I realized that this operator is not the same one. For example, it's the one which is a boosted version of itself, boosted by the H mod symmetry that we discussed. So it's perfectly possible for this operator to be my starting operator. I apply modular parallel transport by some along some closed trajectory, and then after I'm done, I realize that this operator ended up being mapped to this operator. It will always be related by something which commutes with the RT surface. And so that's the effect that we're looking for. And that effect will be the modular Berry phase. It really isn't a phase because it doesn't have to be a U1. It's just some more general modular Berry transformation that we will discuss in a moment. And again, it reshuffles observables on HA by changing their zero mode frame. In other words, attaching a Wilson line of the modular Berry connection. And whatever the Wilson line, whatever the holonomy is, whatever the final Berry phase or generalization of it is, it's always valued in modular zero modes, operators that don't do anything to the RT surface, but they do something to operators away from the RT surface. Now, for Berry himself, we had the parallel transport, which was the horizontal or a horizontal space equation. And that equation was this one. Do you remember that? So now there is a question. Berry had his definition of parallel transport. What is our definition of modular parallel transport? So The answer is, this is the definition, these two equations. I will talk about them in detail in a moment. We will see in a moment that these equations are very natural generalizations of that one equation to the case where we're not just varying a single state, but a whole modular Hamiltonian. And these equations, solving them, will be giving us what the notion of parallel transport in the current modular context. Any questions so far? So we will discuss the meaning of the equations in a moment, but first let's ask why these equations and how are they related to the Berry problem that we discussed in the first hour. So in the Berry problem, our H was given by psi, remember? And therefore DH was just given by d psi plus psi d psi. That was what DH was equal. Okay. So now I have, in my the new definition of modular parallel transport, I have some commutator equations that involve H mod and DH mod and some zero modes of H mod and some statement about V. And this V is supposed to be the generator of modular parallel transport. And the point about solving these equations is finding the V that satisfies all these conditions. So what is this? So DH here never contains the zero mode of phi because phi is independent of the phase of phi. Let me unpackage this statement again. Is it possible that when I find DH, that I find something in DH that commutes with H itself? And the answer is no, it's not possible. It's not possible because the only such thing that I could have, the only ambiguity I have here is the ambiguity of what phase I choose for phi. Okay? If I had such an ambiguity for phi, then even though I have it, it drops out from H. Okay? So this quantity here, H equals psi outer product, is completely unambiguous. And because it's completely unambiguous, it can never, we can never have something which, this DH can never contain a component of itself which is proportional to psi itself. That just will not happen. Because psi is independent of the phase of phi. So in other words, the only way that I could have generated this thing is if there was some phase ambiguity in H. If there was a phase ambiguity of H, then differentiating that phase would give me something proportional to psi. There is no phase ambiguity in H, and therefore I can never have anything that's proportional to psi. So whatever DH is, it can never have any zero modes of H itself. So therefore, this term in the equation here will never appear in the Berry case. Okay. So it's okay in trying to write a generalization of the Berry problem to write down this extra term, which is plus zero modes of H, because these zero modes could never have occurred in the Berry problem at all. So this part of the equation was just not fixed in the Berry case. Now let's talk about what kind of V's I can have to solve these equations. Well, V, the simplest way to try to guess what V could be here is to just write down d psi minus psi d psi. This kind of V will automatically solve this equation, remembering that there are no zero modes. So if you just plug in this V in here, it will automatically give you this d phi. Okay, that's a fact. But this in general, this V in general contains a zero mode if d phi is not equal to zero. So think about what happens if d phi is not equal to zero, if the inner product. That means that this d phi here contains a little bit of it. There is a little bit of it which is parallel to phi itself. Therefore, this thing would contain a phi projector in it, and a phi projector in it is a zero mode of H. So this tells me that that when I write down some attempted solution to equation 1, which but for a general psi, this equation, I may have a solution to equation number 1, but in general I will not solve equation number 2 because V might in general contain some zero modes of H mod. Okay. So there must be some extra condition that would ensure that this V can satisfy equation 2, which is, or condition 2, which is that it should contain no zero modes of H. What condition would that be? That condition would be just d phi phi is equal to 0. If d phi phi is not equal to 0, there is a zero mode. If d phi phi is equal to 0, then there is no zero mode. So the only way that we can satisfy condition 2 is by imposing this condition. And what is that condition? It is exactly the Berry condition. So I hope that I have just told you, I mean, I certainly told you, I hope that I managed to convey it, that these two equations, when you apply them to the case of the Berry setup, where H is the projector onto the ground state, and DH is just this guy here, that's what DH is, then solving both of these conditions is, well, means finding a V. You can find a V like this in terms of the psi, but that's not enough because psi is ambiguous and then V is ambiguous, and fixing the remaining ambiguity is done by condition 2. When you fix that ambiguity to write down V, in the psi language, you have literally imposed the Berry condition. So these are equivalent problems which have equivalent solutions. That is why these two conditions I just introduced are they constitute a generalization of the Berry problem. Okay, so I guess this is summarized here. I am proposing a new notion of parallel transport here, which is modular parallel transport. It's specified by these two conditions, but for the specific case of the Berry problem, it reads this way. And the second condition, that V contains no zero modes, is literally equivalent to the condition that Berry would have imposed. Okay. So I'm going to, I think I have talked for a little over my time. So I'm going to leave this screen for everybody to absorb, and I will talk about the rest tomorrow. Thanks.
Great, thank you very much, Bartek. So are there any questions?
Hi, could you explain again why zero mode are localized along this RT surface?
I'm sorry, can you repeat the question again?
Why zero mode are localized along this RT surface?
Why zero modes localized on the RT surface?
Yes.
The logic of that statement is that the RT surface is the only locus in the bulk which is fixed by that boost symmetry. The boost symmetry, by definition, is keeping some locus fixed. In the case of a 1+1 dimensional Rindler setup, it was literally a point. Now we have a whole boost symmetry which fixes a whole surface. It's only things that localize on the surface that have a chance of not being affected by the boost. This statement is subject to some subtleties that I might want to talk about, but I'm not sure. Maybe this answers your question already.
Yes, helps.
Should I talk about the subtleties or not?
Yes, you can.
Okay, so there is another place. So you have to make an additional statement about where the operator is supported in the bulk, not about the location, but about the size of the region where it is supported. So it's in the Rindler case. Let me go back to that picture. Okay, so we have a symmetry which acts like this. Let's just talk about a 1+1 dimensional Rindler space. The modular Hamiltonian setup is the same thing, just fibered over different points of the RT surface. So let's just focus on a single point of an RT surface where locally things look like this. So this here is like a point on the RT surface, and this one is obviously fixed by this symmetry. But the whole trajectory is also fixed, yes? So another place where zero modes could be localized is this entire trajectory. If you smeared an operator on the entire trajectory, that would also be fine. But you would have to smear it on at a locus which is higher dimensional than this one. So if you somehow manage to convince yourself that an operator is going to be smeared on a codimension 2 surface in the codimension 2 region in the bulk, then it has no choice but to be localized on the RT surface. So you need that kind of argument as well to really say that your operator lives there.
Thank you very much.
Any other questions?
I have one question. Previously, you emphasized that the projection to the code subspace. So in this construction, how such a concept is implemented?
I'll give you an honest answer, which is that we have been in my collaborators and I, in writing papers, we have been just sort of stating that and hoping that it works further. Maybe that's not the right characterization of what we did. We have a boundary picture, a CFT picture of modular parallel transport. And then when we use literally the same symmetry principles to find a corresponding notion of parallel transport in the bulk, then we find some bulk notion of parallel transport. And then there is a question, do they agree or not? And they must agree after you work in the correct code subspace. But we have never verified this because there are no explicit constructions of a code subspace projector anywhere in the literature that I know of. And the words that I used, which is just use whatever states live in the low energy effective field theory in the bulk, is the best that I have seen in any paper that describes how to construct a correct code subspace. So the way I view it is that making sure that the bulk picture we have, that I will talk about tomorrow, and the boundary picture that we have, which I started to talk about today, but I will talk about it more tomorrow, ensuring that those two pictures, the boundary and the bulk, agree is really a condition on what the code subspace projection can be. And if you try any random projector and declare it to be the code subspace, it will just be the wrong code subspace for okay, and you wanted to check, does my candidate code subspace projector really work for projecting to low energy effective field theory degrees of freedom in the bulk? Then you could check that by checking if the bulk and the boundary pictures I present agree. And if they don't, that means that your projector is wrong. So I view it as a condition on what the allowed code subspace projectors have to satisfy. But when you state it as a condition, that means that you cannot sort of verify the picture. There is still one thing that is unfixed, which has to be fixed by self-consistency. And that unfixed thing is the code subspace projection. So we were never explicit about it, but we leave it as something that has to be determined more or less by self-consistency of the bulk effective description and ADS-CFT in general. Did I answer the question?
I'm not sure I understand your point, but will you explain tomorrow more about this one? Or I'm not sure.
I'm not trying to talk more about the code subspace projection. No, I wasn't planning to, but I will. Maybe we can, because I haven't yet told you what the notion of modular parallel transport is in the bulk. And even in the boundary, I only started to sketch it. I mean, I gave these two conditions, but we haven't talked about what their meaning is all that much. We have only verified so far that they agree with the Berry notion of parallel transport in the Berry special case. But I haven't yet told you about why these conditions, what's special about them, what motivates them. So far, I only told you that we agree with Berry, but I didn't tell you anything else. So tomorrow, I'll tell you about the physical significance of this. Then I'll tell you about how to realize this in the bulk. And then we will be really in a position to discuss the agreement between the bulk and the boundary and how that agreement must be mediated by the code subspace projection. If there is, that's the one last missing ingredient that will make these two things match.
I see. Okay, thank you.
Sure.
So Bart, another question I had was, like, maybe I've asked this in the past, I don't remember, but so it seems to me that these modular Hamiltonians, right? I mean, they kind of move in some kind of auxiliary space, right? And so like, I mean, this kind of modular parallel transport, right? In some kind of auxiliary space that's like you're identifying with the bulk. But this identification is not entirely obvious to me, right? I mean, so for example, I would understand the bulk as some kind of RG flow, but here I'm not sure how to make the connection between the two.
I'll get back to the RG flow in a moment. But first, the modular Hamiltonians are moving in an auxiliary space, it's true. We even have a name for it. We call it kinematic space, and it's the space of subregions. So okay. If I work in a fixed global state, that's not true if I am allowed to change states. But if I work in a fixed state, then the only thing I'm doing is changing regions. And so my parameter space is the space of regions. Mm-hmm. And so that's where we're moving them. And now for the RG flow. So RG relates things that are deeper and less deep in ADS. For RT surfaces, this is a statement that one RT surface will reach deeper than another RT surface, or equivalently, it's a statement that one entanglement wedge completely contains another entanglement wedge. So you could study RG by following trajectories that work by taking a given region and just sort of expanding it in all directions. And that's one trajectory. That trajectory will never close if you want a holonomy, but you could close it, but considering two different ways, two physically distinct ways of enlarging the region, such that you start with the same region, you end with a different region. But let's say first you grow it more on the right and then on the left, and in the other case, first you grow it more on the left and then on the right. That's an example of comparing two different RG schemes. And actually the difference between these two RG schemes would literally be a holonomy of the modular Berry connection.
I see. So, but is there a claim that this auxiliary space where the modular Hamiltonians move is identified with the bulk of? Like,
no, we also have, no. We have the same global state, which means we have the same bulk. We're just looking at the bulk in different ways, meaning using different divisions. And the auxiliary space, as you called it, we call it kinematic space, is the space of divisions. We're always looking at the same geometry. We're just dividing it sometimes this way, sometimes that way.
I see. Okay, thank you.
And so instead of change, so that's a difference with, that's the reason why the modular Berry phases deserve a new name. Like, because we're not actually changing anything physically like Berry did. What Berry did was he had, let's say, his magnetic field, and then he would rotate the magnetic field. That's a physical change. We're actually not changing anything physically. We're just sometimes using one division and sometimes another division of the same geometry, and the geometry doesn't know about us.
Right.
So was that somewhat clear why these two conditions are a generalization, are like they reproduce Berry when you apply them to Berry?
Yes, so I think the difference is the zero mode part, right?
There's one difference, which is the zero mode part. This zero mode part could never have arisen in the Berry case.
Right.
And then in this way of phrasing things, we're looking for a V. Now, in the Berry case, we had some psi, yes? And I can always write a V just by writing this expression in terms of psi. So in some sense, looking for a V is equivalent to looking for the right psi. But there is an ambiguity in V. Why is that? Because if I add to V a zero mode of H mod, I will still have the same equation one will still be satisfied. So I need to find a way of fixing an ambiguity of V. Fixing an ambiguity of V is equivalent to fixing an ambiguity of psi. And the way I fix the ambiguity of psi is by imposing this condition. But what condition is that? It's the Berry condition. And so that's the reason why solving these equations involves the same mathematics, the same algebra as solving Berry parallel transport. And that's kind of written here. Okay, so yeah, thank you.
Yeah, thank you very much for the talk. Yes. So I just had one final question. So you said like it's possible that the fibers are non-abelian in this case, right?
Definitely, yes. That's also true in the Berry case. When I have a degeneracy between two eigenstates, then there will be a non-abelian piece.
Right, but in that case, I mean, you consider, like, I mean, the operators are non-commuting, right? I mean, you have a bunch of modular Hamiltonians that are non-commuting in that case, right?
They are always non-commuting. They're always non-commuting. So even in the Berry case, they're non-commuting. If you take, so in the Berry case, like I said, the Hamiltonians are psi. And if I change it into psi plus d psi and psi plus d psi, psi and psi plus d psi, they don't commute.
Right.
The modular Hamiltonians never commute. But the thing that takes you from H to H plus DH, that solves this equation, may or may not be a, I mean, it might just be a U1. In the case of Berry, this is a U1. So the fact that H and DH don't commute doesn't necessarily mean that the Berry phase itself will be valued in a non-abelian group.
I see, right.
However, a lot of the times it will be.
Thank you. Okay, so I think we had quite a few questions. So if there are no more, then let's thank Bartek again for the very nice lectures.
Great, thank you very much. And I will tomorrow wrap up applications to ADS-CFT. I don't think I will talk about quantum computing, but I will talk about the holographically relevant stuff.
Great, I'm looking forward to it. Okay, so thank you all for attending and see you tomorrow.
Bye.
Bye.